Thanks. Is it going? Okay. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. I pray that you be with us today. Help us to just wrap up our thinking about the homework in Chapter 8. And I just pray that you'd help the students to begin to prepare for the test, which is upcoming, that you just draw their thinking together and help them to ask the right questions so that they can just complete their knowledge about this material. Lord, in your name I pray. Amen. So, you guys got questions? Yes?
8.7, question 21.
Oh, yeah. Thomas was just asking me about that before class.
Are we going to have to do that depending on the test?
21 is possibly reasonable for the test if I made it about the trapezoid rule, perhaps. Let's attack that for just a couple minutes. See how bad it is. I thought you were asking me about 31. 31 is yeah, 31. That 31 is ghastly. Integral from, this one's not too bad, I think. Integral from 0 to 2 of e to the minus x squared dx. And we're supposed to find n that gets us what? An error of at most 0.0001. And we are supposed to use trapezoid rule or Simpson's rule. So what n do we need for e n t? That's part A, right? Or the error in the nth application of Simpson's rule, that's part B, to be less than 0.0001. All right, so basically, let me just give you an outline of what we're doing. I mean, so in here I didn't get a chance to do it yesterday, right? That's the thing. So basically, we have those theorems. What was the theorem? If the absolute value of f prime prime of x is less than or equal to m for a less than or equal to x less than or equal to b, then the error in the trapezoid rule of order n is less than or equal to, how's it go? B minus a to the third power divided by 12n squared times m. Did I get it right? Did I get it right? I don't. You guys, so that's the first part of the second part of the theorem, and these are kind of distributed in the section in boxes. The second part was if we have a bound on the fourth derivative, if we can say the fourth derivative is less than or equal to some m, particular constant m, for a less than or equal to x less than or equal to b, then the error in the nth application of Simpson's rule is less than or equal to b minus a to the fifth power divided by, well, obviously 2,880 n to the fourth. I'm ashamed that that number is stuck in my head now. I could definitely use my mental capacity for something more important, like, say, a child's birthday. But now I know this number. Thanks, guys. You did this to me. It's all your fault for taking this course. Let's see here. Did I get those right? All right, so those are the tools we need to work with. These are not easy tools to use, mostly because the actual finding of the bound, now that's what could be hard in certain problems, right? You have to somehow solve this inequality, right? This is the mission, the critical part of the mission that's not immediately easy or just straightforward to do, right? But it's, on the other hand, not impossible, because basically we can use differential calculus to figure that out. Let me show you how. So this problem, we have f of x is equal to e to the minus x squared, right? And this one we have a equals to 0, b is equal to 2, right? Just to get started. And so I'll do part A, and I'm going to leave part B to you guys, all right? So part A, you're like, well, you're doing the easy part. Yes, I know. F prime of x is what? Yeah, minus 2x e to the minus x squared, right? What's the second derivative? E to the minus x squared times what? Times minus 2 plus 4x squared, right? I'll take a third derivative while we're at it. We have e to the minus x squared times what? Times derivative of this stuff, which gives me 8x. And then minus 2x times what's there already. Let me clean it up. So e to the minus x squared so is this 12x minus what? 8x cubed, right? Let's see here. Can we clean up the second derivative? What I've got is I've got I've got 4 times e to the minus x squared times x squared, what? Minus 1/2, right? So I could write that as what? I could do that. I'm not sure if this is helpful or not, but it's something I could do. All right, what's our goal? Our goal is to put a bound on this expression, right? For what? Right. Oh. Well, that's not too bad. Let me show you why. Here's how I'll think about it. If you look at this, right, what can you say about the derivative of f as long as x is not equal to 0? Well, I guess you can say this. If you were to draw a sign chart, right, for this, you've got 0, you got minuses, and you got pluses, right? In other words, f is increasing for negative values, and it's decreasing for positive values. Okay? So if we think about this second derivative, I can say that that's equal to what? That's equal to 4 e to the minus x squared times, I'm going to go back to the x squared minus 1/2 because it's easier to think about. The factoring didn't help me much. I can get away with this. So if I want to make the absolute value of that, right, I want to do what? I'm trying to make this less than or equal to some m. So first of all, this is equal to 4 times the absolute value of e to the minus x squared, to start with, all right? And then that's the absolute value of x squared minus 1/2. I mean, there's various ways to think about this, but I'm showing you a way. What did we just figure out? We figured out that e to the minus x squared is decreasing, right? It's decreasing from 0 to 2. So if I want to make that factor, the first factor, as large as it can possibly be on the interval from 0 to 2, what would I make it? Oh, goodness, I didn't need calculus to figure this out. What's the most that e to the minus x squared can ever be for positive x? Yeah. It's 1, right? So this is less than or equal to 4 times 1, right? And how about the other piece, x squared minus 1/2? What's that look like? Think about just a little picture, if you will. This is a parabola, which opens up like that. It's got a y-intercept of minus 1/2, right? So it's going from minus a half. When it gets to 1, where is it? This picture isn't very good. It's also at a half, isn't it? Yeah. 1 minus a half is still a half. So the largest that factor ever is in magnitude is what? If we just look at this factor right here, what's the biggest it can be? No. Oh, you're right. I'm looking at the wrong interval. Oh, thank you. I'm not supposed to look at 1. I'm supposed to look at what? 2. Oh, thank you. So that would be what? Yeah, 3 halves. What you said is just perfect. It's 4 minus a half is 3 halves. So what's the largest of magnitude it be? Just what the gentleman said, 3 halves. So 3 halves, right? Now.
I don't think that. Yeah, I was still wrong when I told you that.
Oh.
Because 4 minus a half would be 3 and a half, which is 7.
Oh, curses. I wanted you to be right. Let's see here. It teaches me to have faith in people. All right. It's like my grandfather always said, trust the Lord, don't trust people. It's good advice to live by. Let's see here. People will let you down. That's kind of depressing, isn't it? 28 over 2, 14. So m is 14. Are there other m's you could find? Yeah. But it should be at least as big as that. Well, maybe you could find a smaller one. I don't know. Yep.
On the second derivative, when you factor it out like that, I don't see how x squared minus half turns into minus 4 plus 4.
Oh, yeah, I don't either. I was using the new math. Sorry, no, it was just wrong. Thank you. I'm glad you don't see that. You shouldn't see that, yes. All right, that's the first step in the game here for part A. Now what? And here's the thing we haven't done yet. This is the one remaining example I was talking about, actually. What you do then, to find the n which makes trapezoid rule work for this problem, right? You say, okay, so what I want then is I want it to just barely work. So what I'm going to do is I'm going to solve ENT equals to the given epsilon, which was 0.0001, right? But what is that? By the theorem, that's b minus a, which is what? 2 minus 0 cubed, divided by 12n squared. The n I don't know this time. In contrast, yesterday we worked a problem where n was given to us from the outset. See the difference? The m we just found was 14. Right? That's the thing we had to work for. And that's equal to 0.0001. And then you just solve for n, and then use some common sense. Let's see here. So n is what? I'll solve for n squared. N squared is equal to 8 times 14 over 12 times 0.0001. And then, so what's n going to be? Square root of that, right? And maybe I should put an n tilde on there or something. It's not really going to be my n, and you'll see why. It'll become glaringly obvious why that's not n very soon. All right? So what do we get? 8 times 14 divided by 12 divided by 0.0001. Square root of that. 305.5. So, I mean, obviously, can you do a trapezoid rule with 305.5 subdivisions? No. We can only do like 305 or 306. So to be safe, we say, okay, so we'll let n equals to 306. Hopefully that should do it if we believe the theorem and if our math was correct. Let me see if we were so fortunate as to bound the second derivative the same way the book did to find their answer. Where are we? Section what? 8.7 is it? number what? 8.7, number 21. What do we got? What do we got? 8.7, number 21. It's got n greater than or equal to 78. Okay, so we are within the tolerance. As you can see, this you could do better than, right? So it'd be fun to work backwards from the book's answer to see what the optimal m is, right? So as far as the homework goes and as far as the test goes, I don't require you to find the absolute best m. I just require you to find a logical m. Okay? That's very freeing. If this was a course about numerical analysis, or if this was the whole thrust of the course, then I would be pickier, right? But I just want you to have some logical application of the ideas. So your principal tools to work with as you're studying expressions is what? We have the absolute value of a times b is absolute value of a times absolute value of b. We know this, right? Also, this is more useful even. The absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. This is the triangle inequality. These are tools that you can work with as you're studying the inequality. So for number 31, right? Number 31, you're facing, what was it, the integral from 1 to 5 of... I was trying to be nice to you guys by signing ones that were odd in the book, but, well, oh, but they tell you n is equal to 20. But even so, you still have to find the m. So it's x squared minus 4 over x squared plus 9. All right. So let me kind of outline what you do here. So this whole thing is f of x, right? So in order to, and you're given, use n equals 20 and estimate the theoretical error. It's theoretical because there's also an experimental error in the sense that the machine epsilon enters and corrupts. Do you know what machine epsilon is? In Calc 1, we talk about epsilon delta proofs, right? Epsilon greater than 0. Find a delta, blah, 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 blah. Well, there's this thing called machine epsilon. So machine epsilon refers to the smallest possible number you can represent given your computer data type. There is some smallest number that you can possibly represent using binary type, binary object of a particular type. And so arguments below a certain, let's say, granularity are just impossible. So that's limited. That's what, there's a machine error that enters because of that. But anyway, forget about that. So what you got to do, here's an outline of the solution. I'm not going to do it. So step 1, calculate f prime of x, f prime prime of x, and f prime 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 of x, and f prime 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 of x. Actually, this is all you need for, is it for Simpsons or for, is this just for Simpsons? Oh, just Simpsons. Aren't they so nice? So yeah, forget the circle. There is a nicer version of this question that you could ask for trapezoid, right? Trapezoid's nicer because you only have to bound the second derivative, not the fourth. Okay, this is unpleasant for this expression, all right? So you should use Wolfram Alpha or something to check your work, right? I'm totally cool with you using Wolfram Alpha to just write down the answer here. That would be okay with me. Sorry. I didn't tell you that earlier, but Thomas got good practice actually calculating this. Calculating these and checking yourself against Wolfram Alpha will make you stronger. It is a worthwhile use of your time, believe it or not. All right. Once you do this, right, this is going to be some expression like, let me just say hypothetically, now this is not what it is, but let's just suppose it was, 16,672 x to the 5th plus 300 x to the 4th minus 20 x cubed plus 7, all divided by this much I'm sure about, x squared plus 9 let's see, the first derivative makes that a square. The second makes it a fourth. The third makes it a 16? You have fifth? Oh, there's a simplification. Okay. So, well, fifth or sixth, depending on whether you simplify or not, all right? So, well, let's, fifth, but this assumes you've done some algebra. Sixth, if you don't do the algebra, or if you anyway, so it's something like this, all right? So the question then is, you want to find, you want the fourth derivative of x, right? You want to find a bound for that to be less than or equal to m. For what? For 1 less than or equal to x less than or equal to 5. So how do you do something like, how do I bound something like a fraction? I mean, here's some first order. So I'm trying to bound this thing, right? How do you make a fraction larger? You make the what? You make the denominator smaller, make the numerator larger. So what's the smallest the denominator can be? I'm putting in numbers between 1 and 5. What's the smallest the denominator can be? What did you say? You say 10 to the fifth? Yeah. Right, absolutely. See, because x squared plus 9, the smallest that can be is 10. Right? So yes, 10 to the fifth. That's the best we can do, I think, for the denominator. Or 10 to the sixth if you didn't simplify the algebra like Thomas. And then what? Well, then we use the triangle inequality. If you can do it for 2 things, you can also do it for 3 things, or 4 things. And so here's where I'm being lazy. There might be something smaller that's also an upper bound. I don't care about that. I'm just trying to find a logical upper bound. All right. So I can do 16,672 times the absolute value of x to the fifth, plus 300 the absolute value of x to the fourth, plus 20 absolute value of x to the third, plus 7. Now, what did I do? I factored out the 20. Right, so if I've got the absolute value eats minus signs, and you can pull out the numbers, positive numbers, right? How about absolute value of x? What's that? Here's absolute value of x. You're going from 1 to 5 as possible inputs. What's the largest it can be? It's not hard. It's 5, right? So you just take all of these. Replace this with 5 to the 5. Replace this with 5 to the 4. Replace this with 5 cubed, right? So you're like 125, 625, number I don't know. Add them up, bam, m. Then you use the theorem. You should thank Thomas for coming and asking me about this morning. Otherwise, I would have burnt 15 minutes of class time probably. So. That one's tough, I think. Now, those who are more adept at inequality arguments than I am this morning would probably argue what I just did is naive or not optimal, but it works. It's logical. It gets us an m. It may not be the absolute lowest m we could use. I mean, it may, but it is nevertheless a upper bound for the expression, which is what we're looking for. Like somebody asks you, okay, you're a contractor for a construction project. How long is it going to take you to build that intersection? And you're like, less than 100 years. It probably doesn't work, right? But for us, it works. That's what I'm trying to tell you. The fact that 6 months is the actual number you should tell that person, I don't care about that as it applies to this problem. I just want you to give me a logical argument. preferably not something that is like, I looked at the graph, and the graph of the fourth derivative is at most 10,000 or whatever, or I mean, whatever it is. So, enough about that. You guys have other questions? Preferably about integration. I don't really want to talk more about section 8.7 if we can help it. So. So all of the other homework from all the other sections, you guys are just finished, and it's like it's good. And you're fine with it. It's boring. There's no need to discuss any of those things.
Well, 25 on 8.6.
I'm of course being facetious. Let's see here. Yes, 25 on 8.6. I have a strong suspicion this is almost the same as the cosine one we did yesterday. So dx over 2 plus sine x, right? Yeah, yesterday we did cosine, right? Because Dr. Scambordis got me started on it. And like a moth to a flame, I did it. Let's see here. So we must remember what were the takeaway points from the Weierstrass substitution? U is equal to the tangent of x over 2. Du was equal to what? Well, dx was equal to what? Can you guys remind me, it was what? 2 du over what? 1 plus u squared? What was cosine of x equal to? What was sine of x equal to? Cosine was what? 1 minus u squared over 1 plus u squared? And sine was 2u over 1 plus u squared. Am I right? Am I right about that too?
Yes.
Okay. Good. I've got all the necessary 2's. So there you go. There is the Weierstrass substitution. We put the beast in the corner. There it is. But this thing is a machine. I mean, frankly, once you understand this substitution will solve, or at least get us started on solving any rational function of sine and cosine. That's such a stupidly general statement I just made. It means almost every example that's been hard is covered by this thing. That's really nice. Like, for example, I haven't tried this yet, but we might try to do the integral of secant cubed. Remember secant cubed? That one was hard, wasn't it? I wonder how hard it is with the Weierstrass substitution. We didn't try that. But if you believe what I just said, we could. Let's see here. So I will do that in the second section, so I don't have to do it in here. I'm going to do that at the start of class for the next ones, because somebody asked me to. I'm going to do for you guys next, since you're not super pushy about what I should do in here, I'm going to do the hyperbolic analog of this next. But are we so far so good? Did I do something wrong, or what do you think? Does that make sense? I multiply the top and the bottom by 1 plus u squared. This one's a little bit harder than the cosine one because we have what? The denominator in the cosine one worked out so pretty. This is 2u squared plus 2u. Oh, plus 2. Look at that. Look at all these 2's. Let me make them go away. Okay, so how do you integrate 1 over u squared plus u plus 1? Sidebar. So u squared plus u plus 1 is equal to u plus 1/2 squared, right? Plus 1/2. Well, no, that's not true. What's 1/2 squared? 1/4. So that's actually should be what? I should have a 3/4 here, right? or let me write it more interestingly as the square root 3 over 2 quantity squared. There. This suggests a trigonometric substitution by tangent theta. We make a u plus 1/2 equals square root 3 over 2 tangent theta substitution here. So that gives me things like du is square root 3 over 2 secant squared theta d theta. Right? And it also gives me what? The whole point of doing this was that u plus 1/2 squared plus square root 3 over 2 squared gives me what? 3/2. Goodness gracious. 3/4 secant squared theta. So my du is square root 3 over 2 secant squared theta d theta. Downstairs simplifies to 3/4 secant squared theta with respect to this trig substitution. So it's a little bit different than the cosine integral we did, but not too different really. So what do we have? 2 root 3 over 3 theta plus a constant. In other words, 2 root 3 over 3. Solve for theta, what do I have? I've got inverse tangent of what? See this right here? That gives me 2 over root 3 times u plus 1/2 equals to tangent theta, right? So you take inverse tangent of both sides, what do we get? We get inverse tangent of 2 over root 3 u plus 1/2 plus a constant, of course. And then what do we do? Yep. 2 root 3 over 3 inverse tangent of 2 over root 3 times tangent of x over 2 plus 1/2 close parenthesis plus constant. There you go. Wait a minute, was this a homework problem? Oh, I'm sorry. I again have deprived you of joy. Yes?
I don't know how you got 3/4 secant theta in the denominator.
Secant squared theta. Well, that's the whole point of the trig substitution, is that if I make this thing square root 3 over 2 tangent squared theta, when I plug that in, I get like 3/4 tangent squared theta plus the 3/4 that was already there. So I get 3/4 times tangent squared theta plus 1, but tangent squared theta plus 1 is precisely secant squared theta. So it's let me have pity upon you and talk about number 41. So this is section 8.6, number 41. So here you're asked, what's the integral of hyperbolic secant of x dx? Now I have speculated at various points in my life that, you could solve this by using u equals hyperbolic secant plus hyperbolic tangent. I'm not so sure about that. I tried it yesterday. It didn't work. So he says you can integrate it by using a hyperbolic tangent. He says use u equals hyperbolic tangent of x over 2 substitution. In other words, use the hyperbolic analog of the Weierstrass. We call it the hyper-Weierstrass substitution. Well, it's a Homer problem, so let's work it out. So du is what? 1/2 hyperbolic secant squared. I mean, I expect you'd be able to differentiate hyperbolic functions and work with them, so I guess the answer is yeah. 1/2 hyperbolic secant squared dx over 2 dx, right? So that's to you, but that's not terribly useful yet. We need to draw the triangle for the hyperbolic substitution, see what's that look like. Remember we did these a little bit one day, but they were a little bit weird. So if this is x over 2, this is the opposite side and this is the adjacent side, what does that make the hypotenuse if this is with the hyperbolic triangle, let's say, of the tangent x over 2 substitution? Square root of 1 minus u squared, yeah. That is right, because of course we need cos squared. Cos squared minus sinh squared would be 1, so if the adjacent side is like cos and the opposite side is like sinh, then this must be the square root of 1 minus u squared. All right, so that is actually the triangle here. And once you have that, it's easy to write down the formulas for, like, for example, what's cos of x over 2? What's sinh of x over 2? Uh-huh. Right. That is right. Right. Now, let's see, there are some, we're looking for a program of substitution like I have up in the corner there, the hyperbolic analog of that, right? So I need to figure out what's the formula for cos x, what's the formula for sinh x. How are cos x and sinh x related to, like, half of x? Well, there it pays to remember that we have this identity that says that the sinh of 2 theta is equal to 2 cos sinh, right? So what does that tell me? If I put theta equals to x over 2, what do I get? I get sinh of x equals to what? Right, so, check it out. So what we get, therefore, sinh x is what? Sinh x is 2u over 1 minus u squared. So it's an awful lot like what's in the corner over there for our sine integral, but just slightly different, right? There's that 1 minus u squared. Now to figure out cos, I need to figure out what's the formula for cos of 2 theta? How do we figure that out? If you don't remember the identity, but you do remember the one that's in red, a simple thing to do is to differentiate that identity to find the other one, right? If I differentiate the cos 2 theta identity, what does that give me with respect to theta? Let's see here, I get 2 cos of 2 theta, right? On the flip side, I get product rules, right? So I get like 2 sinh squared plus 2 cos squared, because derivative of cos and sinh are, well, sinh and cos. So I could also write this as what? This gives me the identity cos 2 theta is equal to sinh squared theta plus cos squared theta, right? But hey, we can use that, what I just wrote in purple, that's actually, for our current purposes, that's just fine. We can use that to figure out the analog of the formula we already found for sinh. So what is it? So cos x is equal to what? U squared over 1 minus u squared, right? Plus what? 1 over 1 minus u squared, right? So what do we got? We've got ourselves u squared plus 1 over 1 minus u squared. So I'm trying to help you guys out. I'm doing the, you might say, the hard part of problem 41, which is to discover the, the analog of the Weierstrass substitution for the hyperbolic case. And here it is. I guess I still need to clean up this dx. What's dx equal to? 2 du. Right, but what's that? Hyperbolic secant is 1 over cosh squared, right? Right, so it's just 2 du. So but that's squared, so it's this. So I won't finish it, but for number 41 then, in view of that colossal hint I just gave you, if you look at the hyperbolic secant of x dx, we can write it as what? We let x equal, or excuse me, we let u equal the hyperbolic tangent of x over 2. Once we make that substitution, we get what we just wrote over there. So we can do this. This is actually dx over cosh x, right? And so that's what? That's the integral of, apparently dx is what? I need to get glasses or some binoculars. I'm not sure. 2 du over 1 minus u squared, right? And divided by what was cosh x, do we figure out? 1 plus u squared over 1 minus u squared. So I'll just clean it up. We can simplify that. You get 2 du over what? If I write anything more, I will deprive you of the joy. So that's so I'm not terribly surprised, but basically the Weierstrass machine exists, of course, in the world of trig functions, but there is also a hyperbolic Weierstrass substitution, which will also seek and destroy arbitrary rational functions of cosh and sinh. Now, I said, well, this Weierstrass substitution works for any rational function of sine and cosine, right? So you could get carried away, you know? You could get carried away with this. You could be like, integral of tangent x. You'd be like, well, tangent, I know what tangent is. Tangent sine x over cosine x, right? You're like, this is a rational function of sine and cosine, right? It's a fraction of polynomials in sine and cosine. So I can use the Weierstrass substitution. Is this a good place to use the Weierstrass substitution? No, it is not. Weierstrass substitution is an insurance plan. It's a backup plan. If other methods fail, then we'll try the Weierstrass substitution. Here, of course, we should make a u equals cosine x substitution like we did last semester, I hope, or whenever you took Calc 1. That's one of our favorite u substitution examples. Well, one of mine. You guys have other questions? No? All right, well, have a good weekend then.